Welcome to our today's video. In our last video, we looked at a spanning set of a vector space, and today we're looking at a spanning set of a vector. It's like somehow related to the earlier one, but they are different. The earlier one, we're looking at spanning set of a vector space. So just to remind you what we did last time, we're looking at whether a set of vectors spans a vector space. And so we are saying that for a set S, for example, which comprises of vector u1, u2, and u3, for this set to span our vector space, for instance, vector space R3, we are choosing any vector from R3 and seeing whether that vector that we've chosen can be written as a linear combination of these three vectors. So if that happens, then we say that S spans R3. So S would span R3 if any vector chosen from R3 can be written as a linear combination of the vectors in S. That is what we looked at in our last video on spanning set of a vector space. But in today's video, we will concentrate on how do we tell if a vector is in the span of some set, if it's in the span of some set. And so we give by definer to say that a vector U is said to be in the span, this span, if U can be written as a linear combination of these vectors. So if U can be written in as a linear combination of these vectors, then let's say that U is in this span. But if it cannot be written as a linear combination of these vectors, then it's not in this span. A very quick example. Is this vector in the span of this? In other words, can this U be written as a linear combination of these vectors? So, and you recall we did how to write a vector as a linear combination of other vectors. So we seek to find if scalars ABC exist such that A times this first vector plus B times this second vector plus C times this third vector would give us U. If those scalars exist, and then it means that U can be written as a linear combination of these vectors, and therefore U is in this span. So let's just see what we did, what I did to solve this. So what I did is just what I've already explained, that we look for these scalars if they exist. So multiplying that, I have A plus B plus 2C is equals to 1. And then this one I have A plus 2B minus C is equals to -2. And then this one I have A plus 3B plus C is equals to 5. I get this system of linear equations, which we can solve using any method that we know. So far, we've learned so many methods of solving system of linear equations. So reducing, using row reduction or reducing even to echelon form, reducing to echelon form, I arrive at this point where I can see that C can be obtained. Our scalar C can be obtained. So if C can be obtained, then the rest of the other scalars can also be obtained. And so what that means is that my scalars ABC exist, and that U can be written as a linear combination of these three vectors. And therefore, since that is possible, We say therefore that U is in this span. U is in that span. So in this video, we'll move very fast because you already know how to solve systems of linear equations and how to write a vector as a linear combination of the other vectors. And if you do not know that, then it's good you check on my earlier videos on one, on how to solve system of linear equations, two, on linear combination of vectors. And you also can look at spanning sets of vectors. You can check those videos. It can help you on how to solve the system of linear equations. So we've already done that. We've seen that the scalars exist. And so since the scalars exist, we say that U is in this span. We can write it this way. You can write that U is in the span. Is in this span. So you can see that this means element of is belongs to. U belongs to this span. Let's look at another example very fast. So the example that I want us to look at is this. Is this vector in this span? Is it in this span? In other words, can this vector here be written as a linear combination of these three vectors? So we find if we can find scalars such that x times the first vector plus y times the second vector plus z times the third vector would give us U. So expanding this, I would have x plus 2y minus z equals to 3. And then 0x plus 2y minus 2z equals to negative 4. And this one is x negative y plus 2z is equals to 8. So we arrive at this system of linear equations, which we carry out elementary row operations and arrive at this. This is the last column. But what interests me very much is this last row. This last row implies that 0x plus 0y plus 0z would give us negative 1, which is not possible. So that means we cannot find the scalars x, y, and z, such that when you multiply them by zeros and add the result, you would get negative 1. So since these scalars do not exist, it means that this U cannot be written as a linear combination of these vectors. And since that is not possible, we say that U is not in this span. Is not in this span. U is not there. So let's look at another quick example. This time I want to use matrices. You can use matrices, you can use polynomials, it's no problem. The logic is the same. So I'm given, consider this matrix A, B, and the question is, there's also this span. There's also this span. The question is matrix A in this span? What about matrix B? Is it in this span? So these are two questions, and we do all of them one after the other. First, we'll determine if A is in this span. In other words, can you write this matrix A as a linear combination of these two matrices? If that is possible, then A is in this span. And then we come back and determine if B is also in the span. So our solution, we first consider A and see if scalar AB can be obtained such that A can be written as a linear combination of M1 and M2. So this is my A equals to A times M1 plus B times M2. When I multiply this out, I'll get that 1 is equals to A, and get that 2 is equals to B. So A and B exist, and therefore A can be written as any combination of these vectors, of these matrices, and therefore A is in the span. It's in this span. What about B? Is B in the span? So again, the same reasoning. Let's do it. Let's see if we can find scalars AB such that B would equal to A M1 plus B M2. But this is our B. A M1 plus B M2. We find that 0 is equals to A. 0 is equals to A. 0 is equals to A. And also find that 1 is equals to 0. 1 is equals to 0. Because this is 1 is equals to 0 plus 0, which is not possible. And you also see that 1 is equals to 0 plus 0. And also see that 0 is equals to B. So in other words, this system has no solution, because how can we have 1 equal to 0? It's not possible. So we cannot find A and B. We cannot find A and B such that this is satisfied. We cannot find A and B such that this is satisfied. So that what that means is that B cannot be written as a linear combination of this and that, and therefore B is not in the span. B is not in the span. That's what this implies. Let's try the polynomials this time. As I said, this knowledge can be extended to matrices, polynomials, and so on. So this time I want to try polynomials. And the question is, show that this polynomial is in this span. In other words, can this polynomial be written as a linear combination of these other two polynomials? So we require to show that Px can be written as a linear combination of the polynomials there. So we let alpha and beta be in R, and we want to see whether alpha times the first polynomial plus beta that times the second polynomial would give us Px. So we just multiply this. This will be alpha. This will be 4 alpha x squared plus alpha x plus beta x squared minus 2 beta x plus 3 beta is equals to this much, is equals to this polynomial. So at this point we would bring together those that have x squared. We bring together those that have x squared, and those that have x squared is 4 alpha plus beta. 4 alpha plus beta is equals to the other one that is x squared, this side is 5. And then those that have just x is alpha minus 2 beta. So alpha minus 2 beta will give us negative 7. And we also have constants we have this 3 beta, which equals to 4. So this last one tells us that beta can be obtained. And since beta can be obtained, substituting it here, we can get alpha. Let's see, beta here is 4/3. Beta there is 4/3. What would be alpha? So alpha can be obtained. So clearly alpha and beta exist. And since they exist, this polynomial can be written as any combination of these other polynomials. And therefore, this polynomial is in this span. Now, I just want to caution you here. It's good to, after you found beta, find alpha here. And the value of alpha and beta that you have, see whether they satisfy this equation. Because sometimes you might find alpha and beta and then discover that they do not satisfy this other equation. So if they do not satisfy, then it means they do not exist. Because you cannot have one alpha having 2 different values and one beta having 2 different values for the same system of linear quotient. So let's just see if I was, because from here I can see that beta will be 4/3. What about alpha? Alpha will be -7 plus 2 beta, but beta is 4/3. So the LCM there is 3, and this will be -21 plus 8, which is 13/3. 13/3 is our alpha. Let's see if it will satisfy this. 4 times, no, this is -13, -13/3. 4 times -13/3 plus beta, which is 4/3. Does it give us 5? The LCM here is 3. Does it really give us 5? This will not give us 5. But yeah, what I think is that we cannot disqualify this from being in this span because they existed. The scalars exist. They may not be the same scalars. They may not have the same values, but they exist. They exist. So I think the term there is they exist, and if they exist, that is okay. But if they do not exist, they will say that this cannot be written in terms of this. But now it's very interesting. We need to know. Maybe we look at this one later, because I'm seeing that they exist. How do we write this as a combination of this? If they have different values, if alpha has different values, let's preserve this for later. Let's preserve this for later. Maybe I did not form my polynomials correctly to give me the same result. I did not come up with the correct polynomials. It's okay, but that's how we do it. Supposing the polynomials have been chosen correctly, then that is how we would have done it. And because that is a procedure. Let's look at the other example. So this example, let U be this, B that, W that, and M that. Does M belong to the span of U V and W. This one is very easy. The question is, can you write this as a linear combination of these other three? And if it's possible, then M belongs to this span. If it's not possible, then it does not belong to X span. So I did it, and I discovered that the scalars exist, and therefore it's possible to write M as a linear combination of these other vectors, and therefore M belongs to this span. You can try it and see whether you get the same thing. So that is how we find out if a vector is in a certain span. So next time we look at linear independence and linear dependence of vectors.